A supernova is one of the most powerful events a universe can produce, an explosion so immense that for a brief moment, a single dying star can outshine an entire galaxy. It is a dramatic ending of a stellar life, but it is also something far greater than destruction. Supernovae are cosmic creators. They forge the elements that make planets possible. They seed galaxies with the ingredients of life, and they shape the evolution of the universe itself. To understand a supernova, we must begin with the life of a star. Stars exist because gravity pulls matter inward, while nuclear fusion pushes outward. For millions or billions of years, this balance holds. In the core of a star, hydrogen fuses into helium, releasing energy. This steady process is what makes a star shine. Over time, as hydrogen becomes depleted, the star begins to fuse heavier elements. In stars like the Sun, fusion will eventually stop at carbon and oxygen, and the star will end its life more quietly, shedding its outer layers and leaving behind a white dwarf. But in massive stars, those many times heavier than our Sun, the process continues far beyond. The core becomes a furnace where elements are built step by step. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. This is a crucial turning point. Iron is the end of the line. Fusing iron does not release energy. It consumes it. When a massive star builds an iron core, it is approaching catastrophe. The star has reached a stage where fusion can no longer support it against gravity. The outward pressure weakens. The core begins to collapse under its own weight. In a fraction of a second, gravity wins completely. The core implodes, crushing matter to unimaginable densities. Protons and electrons are forced together, forming neutrons, and the collapsing core becomes something like a giant atomic nucleus. The collapse happens so rapidly that the outer layers of the star have no time to respond. Then, suddenly, the core rebounds. A shock wave races outward. Neutrinos flood the surrounding material in an enormous burst, carrying away energy and helping drive the explosion. And the star erupts in a supernova. The outer layers are blasted into space at thousands of kilometers per second. What was once a massive star becomes a glowing, expanding shell debris, a supernova remnant that can persist for tens of thousands of years. This explosion is not just spectacular. It is essential. Supernovae are the primary factories of heavy elements in the cosmos. The gold in jewelry, the iron in blood, the calcium in bones, the silicon in rocks. All of these elements were created in stars and released in supernovae. Without these explosions, the universe would be mostly hydrogen and helium, a place with no rocky planets and no chemistry complex enough for life. Supernovae are how the universe becomes enriched. They scatter heavy atoms across interstellar space, mixing them into nebulae that will form the next generation of stars and planetary systems. In this way, every supernova is both an ending and a beginning. The debris of one star becomes the raw material of future suns and worlds. There is more than one type of supernova. The most famous are core collapse supernovae, the deaths of massive stars. But another type occurs in binary star systems. A white dwarf, the dense remnant of a sun-like star, can steal matter from a companion. As it accumulates mass, it approaches a critical limit known as the Chandrasekhar limit. When it can no longer support itself, it undergoes a runaway thermonuclear explosion, completely destroying the white dwarf in what is known as a Type Ia supernova. These explosions are so consistent in brightness that astronomers use them as cosmic distance markers, allowing us to measure the expansion of the universe itself. In fact, observations of distant Type Ia supernovae were crucial in discovering that the expansion of the universe is accelerating, driven by the mysterious force called dark energy. Supernovae therefore connect not only to the life cycles of stars, but to the fate of the cosmos as a whole. Supernovae also leave behind extraordinary remnants. If the collapsing core is not massive enough to become a black hole, it may form a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Some neutron stars spin rapidly and emit beams of radiation, becoming pulsars, cosmic lighthouses sweeping across space. If the core is even more massive, gravity may crush it beyond all limits, forming a black hole. Thus, supernovae are the birthplaces of the most extreme objects in the universe. They are not only explosions. They are transformations, moments when one form of matter becomes something entirely different. The Crab Nebula, one of the most studied remnants, is the aftermath of a supernova observed nearly 1,000 years ago. At its center lies a pulsar, spinning dozens of times per second, the collapsed heart of the star that once was. Supernova remnants glow in many wavelengths, from radio waves to X-rays, revealing shock fronts, magnetic fields, and turbulent chemistry. They are laboratories of physics on the grandest scale. Supernovae also influence galaxies. When they explode, they inject enormous energy into the interstellar medium. They can trigger star formation by compressing nearby clouds, or they can halt it by dispersing gas. They regulate the life cycle of galaxies, shaping where stars can form and how galaxies evolve. In the early universe, the first stars were massive and short-lived, ending in supernovae that seeded the cosmos with the first heavy elements. Those early explosions changed everything, making possible the formation of planets and the complexity we see today. Some of the earliest supernovae may have been even more powerful than those we see now, known as parent stability supernovae, completely destroying stars hundreds of times the mass of the sun and flooding the young universe with heavy elements. Even today, supernovae continue to occur across the universe. Astronomers discover them in distant galaxies, watching the final light of stars that died millions of years ago. Each supernova is a message from the past, a reminder that the universe is dynamic, violent, and creative all at once. Supernovae are also connected to the cosmic origin of life itself. The elements scattered by ancient explosions eventually became part of new stars, new planets, and the chemistry that would allow biology to emerge. In a very real sense, supernovae are part of our own ancestry. The atoms in our bodies were once inside stellar cores, and many were released into space through these colossal blasts. In the end, supernovae reveal a profound truth. Destruction is not the opposite of creation. In the cosmos, destruction is creation. The death of a star becomes the birth of new worlds. The atoms scattered by an ancient explosion may one day form oceans, mountains, living beings, and minds capable of looking back into the sky and wondering where they came from. Every supernova is part of the universe's endless cycle, turning stellar death into cosmic possibility, ensuring that the story of the stars continues forever.